characteristics that you will be responsible for. The first two were square root functions. So we had to understand how to shift them, left 2, down 1. We had to understand that the negative reflected it over the x-axis, so instead of its eyebrow up, it's eyebrow down. And the 2, instead of going the square root of 1 is 1, the square root of 4 is 2, we double that 1. So the square root of 1 is 1, but we double it, 2. The square root of 4 is 2, but we double it, 4. And we get the graph. Any questions on how to create the graph?
So when you're, I don't know why this always bothers me, with the negative in front, what do you do first? You just forget that until the very end and then you just like flop it?
That'll work.
Okay.
Flop that thing. Flop it.
All right. More specifically, you might say you would reflect. Yeah. All right. So any questions about the domain and range on this one? Okay. My 9th graders. Did you say from negative infinity to negative 1?
Yes.
Yes. So we've got that. We're not going to reverse it. It always goes least to greatest. So if negative infinity is one of them, it must come first. Okay? Cool. That is the one thing that I keep seeing being missed over and over again. And it's really just my 9th graders. My 10th graders, actually, you guys got that.
Yeah, we did.
Yeah. All right. So this entire function is decreasing, so it decreases from negative 2 to infinity. We can obviously tell from the graph there's no x-intercept. But if we were to start to solve this and we plugged in 0 for y, what we end up with when we move the 1 over, it becomes positive 1, and then we divide by the negative 2, we get negative 1/2 equals the square root of something. Is it possible to take the square root of anything and get negative 1/2? No, it's not possible. So in this case, we would see that there is no x-intercept because what we're trying to solve doesn't. Okay? But we could just look at the graph because we have the graph. That would be the best way to do that one. To find the y-intercept, though, we can plug in 0 for x, and that goes away. And so we get negative 2 root 2 minus 1. Negative 2 root 2 minus 1. Now, in behavior, we have talked about this a couple times. We can discuss the end behavior as it approaches positive infinity, y approaches negative infinity. As we approach negative 2, from the right, as we approach it from the right, we get out negative 1. This I'm not going to give you for the square root function, the end behavior, because we're really only looking at one of those ends. Okay? So not responsible for this, not responsible for that.
Sweet.
All right, this one was just shifted up 3, nothing fancy. You could see the y-intercept. You didn't have to plug in. There is no x-intercept. We're good.
Yes.
Okay, graphing absolute value. So we're going to just shift up 1. It's reflected over the x, and it's vertically stretched by a factor of 3. Any questions about the domain and range? Does everybody have from negative infinity to 4?
Yeah.
Yes.
Oh,
Good.
right. So I think that's one of my problems.
Yeah.
Okay.
I always seem like...
It's always least to greatest. Every interval goes least to greatest.
Like when I'm graphing, I feel like I would have gone like... I would have started it at negative... or 0, negative 4 instead of...
And so 0, positive 4. This one stays the same. Okay? Now, when we describe our intervals of increase and decrease, we're going to use those x values to set up those intervals. It's telling me my function is increasing from negative infinity to 0, and my function is decreasing from 0 to infinity. To find the x-intercepts, we can actually plug in the 0 for the y here. And when we do and move that 4 over, we get negative 4 equals negative 3 absolute value of x. Divide by negative 3, so 4/3 equals the absolute value of x. So x could either be positive 4/3 or negative 4/3. Y-intercept is 0, 4. And as x approaches positive or negative infinity, y approaches negative infinity. Now, we can use this same kind of absolute value graph to solve absolute value inequalities. Okay, so here I have 2. And let's remind ourselves real quick. Let me erase all the answers real quick. Remind ourselves how we would solve this with a graph. So to solve this with a graph, here's the function. We want to know where it's greater than or equal to positive 1. So here's positive 1. Where is it above that line? It is greater than or equal to positive 1 from here to here. See, that's where it's above that line. So that would be over the interval from negative 1 to positive 1. Does that make sense graphically? All right, this one. Where is this function less than negative 2? So now we're looking at a different line. Negative 2, y value is right there. Where is it less than that? It's over here and over here. So that would be from, you're right, negative infinity to negative 2. Union with 2 to infinity. Now we also solved these same problems algebraically. And let me erase the work and we'll go back through both of these algebraically. If you didn't have the graph, what do? Well, you get the absolute value part by itself. You move the number over. You divide by negative. What happens when you multiply or divide by negative when solving? It's going to flip it.
You only do that if the negative 3 is negative, right? On the.
If you're multiplying or dividing by negative, so I was dividing by negative 3.
Okay,
Yeah.
so it doesn't matter.
Doesn't matter if this one's negative. What matters is if the number that you multiply or divide by. Good questions. Okay, so all of this has to be less than 1, or all of this has to be greater than or equal to negative 1. So once we have this isolated, you set this less than or equal to 1, and then this, change it, and opposite. So is it possible for a number to be less than or equal to 1 while also being greater than or equal to negative 1?
Yes.
Yeah, this comes together, doesn't it?
Yes.
So it goes from here to here, which we could write as a single compound inequality. Couldn't we?
Absolutely.
So you could write your answer either way. Now this one, when we go to solve it, and guys, we already knew the answer to that was going to be that, right?
Yes.
Because we'd already investigated the graph. So we know the answer to this one is going to be this. All right? But to solve it, we would move the 4 over, divide by the negative 3. We're dividing by a negative. So x is greater than 2, or x is less than negative 2. Is it possible to be greater than 2 and less than negative 2?
No.
No, so this does not come together. This goes apart. And so our answer would either be written this way as an inequality or that way in interval notation. Are you with me?
Yeah.
You're zoning in and out.
Yeah.
Yeah. Too many carbs at lunch.
I didn't have my Coke.
Oh, yeah.
It was rudely stolen. Twice today.
Suffering.
I've had 2 Cokes stolen from me.
He freaked out.
All right.
He had a breakdown. He started crying. He actually
I didn't cry.
Yeah.
Okay.
I
Take a look at 4, 5, 6, and then we'll talk about 7 and 8. So take a look at 4, 5, 6. See if you have any questions about those.
I actually really like those. Actually pretty good.
Cool, dude.
But I had no idea how to do it before the quiz until someone showed me, and then I knew it. And now I'm good. Now I'm rocking and rolling.
Awesome.
Cool. That is
Rock
so
and
Yes,
roll.
Sid.
And the solutions for the ones above,
How does it feel,
like
right?
when you found 2, you
Constantly.
knew it would be positive 2 and negative 2 because it's an absolute value, right?
Correct. I'm going to do this absolute value also because it's a little different.
Because it's shifted, right?
Because of the horizontal shift, yeah, it's going to change how we solve it a little bit. It's a good one to look at. We'll look at that one next. These absolute value we could also write as piecewise functions, couldn't we?
Yes.
All right.
Oh, yeah.
Yes.
I remember doing that.
On the next page. Okay. Now on both of our greatest integer, aka step functions right here, our domain is a set of real numbers. On this one, because we're jumping up by 1, the range is a set of integers. But on this one, we're jumping up by 2. Now, because we start at 1, when we jump up by 2, we go 1, 3, 5. What kind of numbers are those?
8.
Odd. So this is a set of odd integers. What if there had been a shift here of positive 4? It would be the set of even integers if this was even. All right. Now, if we have something other than 2 there, where we can't describe it, or 1 or 2, where we can't describe it as a set of integers or a set of even or odd, we can give a pattern. Yeah, so if we had like a 3 here, and we shifted up 1, we'd obviously start at 1, and then we jump by 3, and show the pattern.
1, 4, 7. Okay.
Do you guys remember doing all that?
Yeah.
I think so.
Okay. Any other questions about these? Any problems with the cubed roots? Yeah.
For number 6,
Okay.
we like solve for the x-intercept because I was confused about that.
Sure. If we solve for the x-intercept, we plug in what for y?
0.
0. So we get 0 equals, trying, the cubed root of x plus 2. So we move the 2 over and we get negative 2 equals the cubed root of x. So to solve for x, we would have to cube both sides. I'm trying to draw parentheses. Moby's just being ugly. All right, so we cube both sides, and negative 2 cubed is negative 8.
Okay.
And that's how we get the x-intercept. Yes, ma'am.
How many points will we have to draw on our test?
3.
5 would be good.
5 would be great, but 5 may not always fit. So at least 3. If 5 would fit, that'd be awesome.
If we like draw the middle 3, like on
Yeah.
that one, and we didn't draw the other 2,
Because they're not on the graph.
but we like drew our graph
Yeah.
kind of how you have it. Like,
Yeah, as long as it's going, the concavity is correct on each side, you're good.
Would you count this wrong? Like how I drew my lines on this one?
Well, I mean, you can
That's kind of right, but
Okay,
it's not really the right way.
you drew, instead of a cubed root,
Yeah.
you drew a cubed function instead of the root. You made it go like this.
No, it's like a square over the.
So
That's like a cubic, not a cube root.
have we done this?
Yes.
Plus y
When we did higher degree polynomial functions, we did. When
Okay.
we checked to see if they bounced or they passed.
But I got
looked
this
at
one
the
right,
index.
right?
You did.
So I just drew
You
this one
just-
wrong.
The cube roots are going to open left and right like these do.
Okay, thanks.
Okay?
I don't even follow it.
Alright, so let's go back and take a look at this one. And let's say we were solving this inequality with this absolute value. Absolute value inequality. So this part of the function matches that, and we just want to know where it's greater than or equal to 1. So if we drew in our little line right here, there's 1, so it's greater than here, and it's greater than there. So we can tell from the graph what the answer is. But if you did not have a graph, the way you would solve it is move your everything over to the other side. And now once we have it like this, if all of this in here was greater than 3, would this be a true statement? So this needs to be greater than 3. Or guys, what if all of this in here was less than negative 3?
So you would have to.
It would be.
Because then the next thing you do is take the absolute value. Would the absolute value of less than negative 3 still be bigger than 3?
Yes.
Yeah. So we solved these two. All of this is greater than or equal to 3, or all of that is less than or equal to negative 3. Because if this were negative 4 in here, simplified to negative 4, is the absolute value of negative 4 greater than or equal to 3? Yeah. So that's why you split it algebraically. So we get that x has to be greater than or equal to 0. Is that what we had on our graph?
Yes.
Yeah. And we also get that x is less than or equal to negative 6. Is that what we have on our graph?
Yes.
Yeah. Now we cannot write this as a compound inequality because it's going in opposite directions. Compound you can only write as a single compound inequality if they come together. This one's going apart. So that's the best we can do in inequality notation, written as an inequality. In interval notation, it would look like this. From negative infinity to negative 6, union with from 0 to infinity.
Is there like a calculator part and a no calculator part?
Yes, there is. And all that we've done so far would be on the no calculator part. Any graphing, anytime I'm testing graphing, can you graph? I'm not going to let you hold a graphing calculator. Obviously, the ones where you had to use the graphing calculator to find the intersection, you'll have the graphing calculator. All right, let's take a look at the piecewise next. Now, this first part was just testing, okay, do you know if given a value for x that you plug it into the different pieces of the function to find your y? That's what 9 and 10 we're testing. Please check 9 and 10 now, see if they make sense to you.
I thought I got number 11 wrong. Because then we're off this graph, like, no, I went on the graph.
Yeah.
That scared me.
You guys play Monday's Mill?
Yeah.
Are they good?
No.
They're terrible at golf.
I'm terrible at baseball.
So on these ones, you're just finding which one it satisfies, and then you just
Plug it into that one.
Golf on straight reasons.
That's exactly right. Like this one, x equals 2, where would that go? Oh, it goes into this one. Because this includes an x value of 2. So what is the opposite of 2 squared? Well, 2 squared is 4. The opposite of that would be negative 4. So f of 2 is negative 4.
Oh, I did that all wrong. You plug it into the left side first with that number.
Yeah, you look at the x values you're given, and you look at these restrictions, and then that tells you which function which piece it would fall within. You want me to talk you through another one?
I was plugging it into the equation, then doing my answer into the. Does that make sense?
Like, let's go with x equals 0 on this one.
Okay.
Do you see that x equals 0 falls within this range?
Yes.
So if I plug in 0, I get out 2. Okay, now let's look at another one. X equals 2. Well, let's do this one. X equals 2. Do you see the equal 2 there? So if I plug in 2, I get out 2. Let's do the last one. X equals 6. Well, 6 is going to fall in here. The equals 6. So we plug in 6. 6 cubed is 216. Minus 6 is 210. So when you plug in 6, you get out 210.
And you only have to find the one that fits into?
Yeah, it's only going to fit in one. If it fits in more than one, then this is not a piecewise function.
It's incorrect.
It doesn't pass the vertical.
It would not pass the vertical line test. All right. Okay, any issues graphing piecewise functions?
Not really. He's a piece.
Awesome. I can't wait to grade this test. All right.
I thought I got 11.
This one had some problems.
Miss Wilby.
And the problems that this one had were really teacher problems. What I did was I gave you a situation that was discrete, didn't I?
Yes.
I gave you purchasing items. Okay, let's say we're all buying a new swimsuit for this summer. We can only buy 1 or 2 or 3. You can't buy a third of a swimsuit. So writing it like this is actually incorrect because that's continuous, isn't it? Now, if I had been slightly more thoughtful, I would have given you something that was continuous, something that was measurable. Like if I gave you distance or time or anything that's measurable. Then writing it as an interval or an inequality definitely works. But on this one it didn't. To write this as a piecewise function, whether I purchase 1, 2, 3, 4, 5, or 6 items, I have to pay, was this shipping? $25 shipping. And then after the first 6, do you see how I have to subtract away 6 from this?
Yes.
After the first 6, oops, I erased my answer. Then, so this is x minus 6, then we would pay an additional $4. Yes, sir.
The function I used for everything that was after 6 was 4x plus 1.
Oh, yeah. This simplifies to 4x plus 1.
Yeah, I'm sorry.
So you are 100% accurate. But what we really couldn't do is say x is greater than 6. We would have to say all integers greater than or equal to 7, or all integers greater than 6, or all whole numbers greater than 6, or all whole numbers greater than or equal to 7. We'd have to define it as a discrete situation. I guess we could have written it like this also, couldn't we? We could have gone 7, 8, 9, ... Could we have done that?
Yes.
Yeah. Shown that it was all integers that were greater than 6. Yes, sir.
On number 11, are we going to have any that we only can like put one point on the graph?
Hold on one
'Cause I
second.
wasn't
Let me
sure.
go back
I didn't
to
think I
number
got that-
11.
I didn't think I got that right because of,
Where there's only one dot on the graph.
yeah.
I will try, but when I put little graphs on there, sometimes it's difficult,
Okay.
and sometimes they are on the edge.
Okay.
It's okay.
I'd definitely be lenient on the slope on this one,
Okay.
because there's no way you can accurately display the slope, but
You could like make each y value go up by 2 instead of 1.
Probably.
That would make it.
Sid.
okay, I like it, Sid. Alright, so on this one, can you evaluate given a piecewise graph?
Absolutely.
And this one asks about the extrema. Well, we have the absolute max right here, but we also have a relative max here and a relative min there, don't we?
Yes. Because we have 2, 4. Right?
So 1, 2, 3, absolute max, relative, relative.
Relative minimum.
That's right, relative max, relative min. Okay, so check the rest of number 14 and see if you have any questions about that piecewise graph
Plus 2.
and the information you were to
Got it right.
discover from that.
Got it right. 1, 4, 3.
Yes, Natalie?
On the quadratic one, I thought it would be x is greater than or equal to -1 because it's color.
It certainly could be. It just depends on where. If I put the equal to there, I wouldn't there.
Okay.
Either way is accurate. If you put just less than there, then you definitely could have less than or equal to there. And I'll grade it correct either way because they're both correct options. Yes, ma'am.
For the first equation, x plus 2,
Yes.
I put x plus 2 plus, like x plus 2 in parentheses, that's plus 2. What? Is that wrong?
Okay, if you put
Oh, I see why that's wrong. Oh, if it's on the y-axis and it doesn't have.
yeah, if you shifted it, you were writing it as a shift, which is totally fine. So, but you wouldn't have the y-intercept would be right here. So it would just be x plus 2, not plus 2, because that would have it right here.
Wait, so how are you supposed to do it?
Just slope intercept form.
Like flip it.
Where if I continued it,
Where would it?
the slope is up 1 over 1, up 1 over 1,
And then the x-intercept there would be 0. So that's
and that, yeah. Yes, sir.
If you have an absolute max and a relative max, do you still have to know them both? The question.
I'll guide you by the number of blanks. These are all extrema, really.
So you don't need all of these. Well, you might.
You really kind of should.
Okay.
Okay. All right. So what we have here in blue is the work for how you get the answer. Remember the right side with the absolute value. You take the absolute value symbols and turn them into parentheses, and that gives you the right side when you simplify. With the left side, you have to do the opposite of everything that was in the absolute value, and then simplify. So here's the work for the right side and the left side, and here's your simplified answer right there boxed. Yes, Sid?
I went ahead and drew a graph and then worked off of that.
That works?
Will I be able to do that on the test?
You can sketch a graph, sure, Sid.
Alright, thank you.
If you like that better, do it that way.
What? Have you been doing my pickaxe?
No, yes.
Is that your pepper?
Okay, let's take a look at this. Odd, even, neither. We learned to determine symmetry of a function, whether the symmetry was even or the symmetry is odd, two different ways. One, by looking at the graph, so it could be on the graphing part of your quiz, test.
There's
excuse
two
me.
parts?
Yes.
Is it 2 days? Or
No, it's 1 day.
Okay.
Let me explain. The test tomorrow is a shorter test. It's 1 page, front and back,
Oh.
and then just the front of a half sheet.
Okay. Okay.
So it's probably the shortest test you've taken all year. It's one that you should do extremely well on, considering everybody did really well on the last quiz. I'm hoping for
87.7.
more good grades. But like I was saying, this section right here could be on either part of your test, because we learned to do this graphically. If it's symmetric to the y-axis, then it has even symmetry. If it has rotational symmetry about the origin, we say that the function has odd symmetry. And if it's neither of those two, then we'd say neither. Now, we also did this algebraically by plugging in the opposite of x. When you plug in the opposite of x, if you get out the original function, like on number 17, plugged in negative x, got out what I started with, then it's even, like you do on number 18. Plug in negative x, get out what you started with, it has even symmetry. But if you plug in the opposite of x and you get the opposite of the entire function, then the function is said to have odd symmetry. So if I plug in negative x and I get the opposite of everything, odd. If I plug in negative x and I get out the opposite of everything, odd. Now, if there's more than one term, we ought to be able to factor out that negative, where you see we get the opposite of the original function. Remember how that one problem we factored out the negative out of the top? But we also had a negative in the denominator of that fraction, and so those negatives actually ended up canceling, and it was an even. Had even symmetry. Okay, so take a look at these, see if you have questions. Yes, ma'am.
I have like a question about how you would show it. So if it was on the graphing part, you would just like give us a graph and then just ask us to show you if it's odd.
Either that or I'd give you a function and you could type it into your graphing calculator
Oh, okay.
and sketch a quick graph and then tell me what you think.
Okay, thank you.
Sure the treasury is.
The treasure is.
Sorry, I just read it.
Oh, she did get class officer.
Yeah.
Congratulations, and
Thanks. I remember
are you looking forward to working hard?
Oh, yes, I am.
Good.
Of
course she is.
I thought you said, oh,
Yes. I was a little concerned, honestly, when I walked around at the number of people that did not finish this section. That was somewhat surprising. So, please take a look at these. Yeah, this one's no solution because this ends up being imaginary. Yeah, no solution.
So mad. I got that far and didn't
Okay.
try anything.
So, for most all of these, we're going to use substitution and then solve for x. So, we use substitution. This one we have to square both sides, set it equal to 0, factor it. And then we have to test our answers in both.
Oh, and both?
Both. Because sometimes we get extraneous solutions.
And
And it might work in one but not the
I
other.
didn't do
So always test in both. Don't let it surprise you like this one right here may have. 5/4 didn't work for both, did it?
No.
No.
And it didn't work on the one that I tried, so
It's okay.
I should
I
try.
got confused on half of those.
I got confused on.
I did not do good enough.
No, dude.
I was
Oh, wait,
really
no, I
confused
didn't.
number
I got that
26. I got 2.5, but I think I did it wrong because I just canceled x. Get rid of x.
Okay, on this one, you set these two equal to each other. So I moved my numbers over here, and I moved my square roots over here. So do you see that these are, what's under the radical is identical?
Yes.
So when I subtract this, I subtract one more from this, so it makes -3 roots of x minus 1. So then I divide by -3, square both sides. You get x minus 1 equals 1, so x equals 2. Plug back into both to check, and you get 0 both times. So 2, 0 is the intersection point.
So the first step in 29 is you have to move the 1 over to the other side. Because you can't, if you square it, then you have to square both.
Correct.
that side.
When you have one that has the radical here, if there's anything extra, move it to the other side before you square. Otherwise, it just gets uglier instead of nicer. So, like on this one, we need to move the 2 over before we square both sides.
Oh, I like this next.
I thought that, but then I got stuck.
Okay, so like a lot of, whenever we do like a lot of the graphing ones, they're actually on the graph calculator, finding the intersections, they're not a lot of times going to be like an exact point, right?
Correct.
Okay.
The ones that I give you calculators are probably going to be ugly numbers.
Okay.
Now, 31, you may have seen this one real clearly, but not looked back for this one. But I looked at this, I'm like, oh, that's an exponential function that would have an asymptote at
I had no idea what
1, because we just finished graphing exponential functions, e to a power, in our previous unit,
Yeah.
the logarithmic exponential unit.
What do you bet?
Yeah. So there's one over here that is this answer, so those actually should go together.
Because I saw it and I wasn't sure if it intersected, and I wasn't sure if it would tell me that it did, even if it
It did. It may not have been the easiest thing to find.
Yeah.
Yeah, I had to work a little bit. I knew it was there, though.
Yeah.
Countdown.
Juggling calculators.
Are you going to tell us how many decimals to write on the...
I will.
Okay.
Oh, that's
Yes,
why.
Natalie.
Like how off are you allowed to be like on the numbers?
We definitely should have the same hundreds. After the hundreds, it might go off a little bit due to the number of pixels you have on your screen. Are yours close enough to the hundreds?
Well, on 31,
Yeah.
like it's like the same, but then on 30 and 32 is kind of different. The same tens number,
Okay.
but the hundreds is different.
Let's graph one of these in just a minute, and let me come check it out and see what's going on. Okay, any other questions? All right, I'm going to quit recording then for all those people listening.
Hello?
I'm gonna listen to it.
Good one.